Okay, I hope you're all doing well with the potential energy problems. Um, for today, I want to finish up this whole discussion on gravitational potential energy, and then I'll give you some more problems to try. Tomorrow, I think we'll use that as a day where I'll post all the answer keys, and you can check with your work and check in with me to see where you went wrong, where you went right, and all that good stuff. So, let's come back to this equation, which you remember is just initial potential, initial kinetic plus initial potential. Notice it's plus, but it's plus a negative value, equals final kinetic plus final potential. So if I launch a rocket at velocity v from some radius from the center of the Earth, maybe it's the surface of the Earth, so radius is just radius of Earth, is going to equal the final kinetic plus the final potential. So if I give you, say, a final velocity I'm looking for, maybe a final velocity of 0 because it stopped, you can find the radius, the height at which it has gone. Remember, again, that radius is from the center of the Earth, not the surface. I could also maybe give you a radius, a height the rocket goes to, and you can find its velocity at that height, or some such. Now, for today, I want to talk about escape velocity. If I got a rocket on the surface of the Earth, so this much potential energy, I want to launch it with some velocity such that it completely escapes the Earth. What does that mean in terms of the energy? Well, if it's escaping the Earth, let me come back to my drawing here from yesterday. Recall that potential energy, at infinitely close to the Earth would be negative infinity, but you can't get there. We're here on the surface of the Earth, right here on the potential energy curve. So if I launch a rocket with some kinetic energy, velocity upward, it's basically going to slide up this potential energy graph as kinetic turns into potential. And maybe I gave it enough kinetic to get right here. So it stops there at that height. This is radius from the Earth. This is potential energy. So maybe it'll stop there at wherever I said this radius, this height, and then fall back to the surface. What if I give it more kinetic? Well, then it'll slide further up the graph, reach this height before it falls back. Notice it's falling back because its velocity at that point drops to 0. But its potential energy is still down in here, non-zero. So what does it mean to escape the Earth? What that means is that you would reach infinitely far from the Earth. You would never turn around and fall back to Earth. Or a more mathematical way to say it is you would reach your velocity of 0. In my examples, I reached a velocity of 0 here, or wherever. For escaping the Earth, you would reach a velocity of 0 only at an infinite distance away. So, velocity is 0. That means 1 half mv squared is 0 at an infinite distance away. Let me come back to my page here. At an infinite distance away, radius is infinity. Now, dividing by infinity, at least in the limit, as we saw in the graph, we get 0 here. Okay? So, for escape velocity, my initial velocity, whatever it is to escape, plus my negative potential energy at the surface of the Earth, where r is the radius of Earth, is going to equal a velocity of 0 here, plus this negative, 0 value here, because the infinite radius gives you 0. So, scrolling down, escape velocity, the speed you need to escape Earth completely. So at that point, the right-hand side just reduces to 0. You have 1 half mv squared minus gmm over r. Notice the m's, the lowercase m's cancel out, and I drop them from the equation, equals, final 1 half mv squared, but v is 0, minus final gmm over r, but since r is infinity, that's 0 too. The right-hand side reduces to 0. And now, this velocity value, when I solve for it, will be the velocity needed to attain that 0. In other words, to escape the Earth completely, or what we call escape velocity. So let's just rearrange the equation to solve for v. Okay, I'll let you do the algebra. If we were in class, I would show you the algebra on the board, but no need for that. The velocity of escape from Earth, sometimes we subscript the velocity with an ESC on it. The equation editor gave me a hard time, so I didn't do that. The escape velocity v equals the square root of 2gm over r. So plug in, well, the value of g, the mass of the Earth, and the radius of the Earth if you're launching from the surface. If you're launching from some height above the surface, the radius is going to be radius of Earth plus that height. But let's just talk about from the surface of the Earth, because that's usually what we do. We can plug in the mass of the Earth and the radius of the Earth and find the escape velocity, how fast you have to be going in order to escape Earth. And it ends up being a rather large value. It's either 11 kilometers per second or 14 kilometers per second, somewhere in that ballpark. But so you have to be going that many kilometers per second launching from the surface in order to totally escape Earth. And again, all that means is that as you rise up, you're going to slow down further and further, but you wouldn't reach zero velocity until infinite distance. Or another way to say that is you never come back. By the way, note that spacecraft that we actually launch from Earth never reach escape velocity. Because, at least the surface escape velocity, because they're firing thrust as they're rising up. So all they really need to do is achieve escape velocity for the altitude at which they stop burning their rockets. This escape velocity that we calculate here would be if you were to launch something, just like fire it out of a giant cannon from the surface. This would be the velocity you would need. Actual rockets, since they're firing their thrust at higher altitude, they have a larger R down here, so therefore a smaller escape velocity from the altitude they're at. Now, interesting little side note here. If you look back to your orbital motion equations, the velocity you would have orbiting at some radius was just the square root of gm over r. So if you are in orbit, so maybe you're in a low Earth orbit around Earth, and you want to escape Earth, you would have to change your velocity from square root of gm over r to this escape velocity, square root of 2 gm over r. Or in other words, in order to escape from orbit, you have to increase your velocity by the square root of 2 times. Okay, so if you ever find yourself orbiting a planet and need to escape, that's how you do it. So yeah, some of your homework tonight is going to be calculating some escape velocities just to make sure you're good with that. If you want to do the escape velocity from Mars, you plug in the mass of Mars and the radius of Mars. Since Mars is a much less massive planet, its escape velocity is going to be smaller than Earth's. You can do the same thing for the Moon and get escape velocity from the Moon. And again, since it's much less mass, it's a much smaller escape velocity. That's why to escape Earth and get to the Moon, they needed those giant Apollo Saturn rockets. To escape the Moon, they just need a little thrust from the stupid lunar excursion module they had. If you ever watched the video of those moon landings, it didn't look like a whole lot of rocket firing there, and they just escaped the Moon. They didn't need the power because the escape velocity is much smaller. Now, another interesting little thing that comes out of this is, imagine you have a massive object like our sun, and you shrink its radius. Its escape velocity gets larger because you're dividing by a smaller number. So I can shrink a sun or a star down further and further and further until eventually escape velocity becomes so large it exceeds the speed of light. Now, at that point, since we know nothing can go faster than light, once your escape velocity is the speed of light or greater, nothing can escape. You're trapped in there. Once you go there, you'll never get out. Even light from the surface can't escape. And so we'll never see what's going on in there because the light from it isn't getting out. So we refer to an object like that as a black hole. And a guy named Karl Schwarzschild actually calculated this even before Einstein did relativity. It's actually calculatable from Newtonian mechanics. What we often talk about is, given a constant mass of an object like a sun or a star or whatever, we want to solve for what radius it would have to collapse to in order for the escape velocity to be the speed of light, c. So let's plug in and solve for the radius. Okay, again, plugging in velocity is now c. To solve for radius, we would square both sides and then multiply by r divided by c squared, and we get this equation at the bottom. The Schwarzschild radius of a black hole is equal to 2gm over c squared, where again c is the speed of light, g is a constant, and m is the mass of the star or whatever collapsing. You can do it for any object. We could calculate the Schwarzschild radius of Zoe if we wanted to crush her down to an extremely small size and make her into a little mini black hole. You do it for the Earth. I think you use something like 8 millimeters. So if you took the entire mass of the Earth and crushed it down that it was only 8 millimeters in radius, the escape velocity would be greater than the speed of light, and the Earth would be a little mini black hole. And by the way, this is how you spell Schwarzschild, which is German, so they spell things weird. You take a sun like our sun, plug in the mass of the sun, you can find its Schwarzschild radius, how far it would have to be collapsed in order for it to become a black hole. In reality, of course, stars the size of our sun don't have enough gravitational force to collapse themselves down that far. They actually stop collapsing at white dwarfs. But very, very massive stars, much larger than our sun, when their nuclear fusion ceases, the core collapses in on itself, and if they're massive enough, the gravitational force is enough to crush them down below this radius, and they become a black hole. So again, you can calculate this radius for any object in the real world. There's maximum limits, and those limits are calculatable from general relativity, which we're obviously not going to cover here. So that finishes off the lecture on gravitational potential energy. I'm going to give you a few problems to do tonight that kind of go along with the ones you did yesterday. The main thing here is I'm going to focus on calculating escape velocity and Schwarzschild radius. Then tomorrow I'll upload the answer keys for both, and you can see how you did, and we can go over it and deal with it from there. After that, I want to maybe do an overall review of the whole gravity stuff from after the last quiz on to now, and then we'll have another quiz. All right, so do the worksheet tonight, and I'll talk to you tomorrow.